In this video, we will look at some special types of functions, which include the self-inverse function, the piecewise function, and periodic functions. For some functions, if we derive the definition of its inverse, we will find that the definition of the inverse function is exactly the same as the original function, or fx equals to f inverse x, and they possess the same domains. These kind of functions are called self-inverse functions. An example is the function fx equals to 1 plus 1 over x minus 1 for the domain of x more than 1. If we proceed to evaluate the corresponding inverse function for this function f, we will see that f inverse is exactly the same definition and the same domain as f. Thus, we can say that since f is equals to f inverse and the domains are the same, f is a self-inverse function. One important property of the self-inverse function is that if f is a self-inverse function, then the composite function ff will be the same as the composite function f inverse or f inverse f, which means that ff is equals to x. This property is very useful when evaluating high-order composite functions, such as f200x. If the order is an even number, say f200, we can slowly reduce it from f200x to f198x to f196x, and so on. Eventually, it becomes f squared x, which is the same as simply x. Likewise, if the order is odd, say 201, we can slowly reduce it until it becomes just fx, as shown over here. In example 1, we are asked to find the inverse of this function fx over here, and thus find out the value of f123 of 1. So sort of this gives us a hint that it's going to be a self-inverse function where we can reduce the powers by using the property of the self-inverse function. So let's proceed to find out the inverse of f first. We can let y equals to fx. So we get y equals to minus 3 minus 2x divided by x plus 2. And xy plus 2y will be equals to minus 3 minus 2x. And if we factorize out the x terms together, we'll get x multiplied by y plus 2 equals to minus 3 minus 2y. And therefore, x equals to minus 3 minus 2y over y plus 2. And from here, we also need to find out the range of f such that we get a domain of f inverse. Let's draw the graph out. If we just plot it on our GC, we can see that there will be two asymptotes. X equals to minus 2 and y equals to minus 2 as well. And the graph looks like this. And therefore, we know that the range of f, which is equals to the domain of f inverse, it will be minus 2 to infinity, which is exactly the same as the domain of f. Therefore, we can conclude that f inverse x can be mapped onto the exact same definition, minus 3 minus 2x over x plus 2 for x more than minus 2. And thus, we see that f is actually a self-inverse function. And therefore, we know that since f is a self-inverse function, f of 1, 2, 3, 1 is the same as f of 1, 2, 1 of 1. And if we slowly evaluate it, it will be the same as f1, which is minus 3 minus 2 over 1 plus 2, which gives us minus 5 over 3. A piecewise function is simply a function that has different definitions for different intervals of the function. Meaning to say, it is made up of a few pieces of definitions instead of a single definition. And we can represent piecewise functions by using a big curly bracket and consolidating all the separate functions with their corresponding domains, like this. For example, we can have a piecewise function defined like this. And what this means is for any x value that is less than 0, the function is defined as x squared. For any x value that is between 0 to 2 pi, we are going to substitute the x value into sine x instead. And if x is more than 2 pi, we are going to substitute into the function definition of minus x plus 3 pi instead. So graphically, this function will look like this, where the x squared part is represented by the red curve, the sine x part is represented by the sine curve, and finally, for anything larger than 2 pi, it is represented by this straight line over here. In example 2, we are now asked to find out the inverse function of this piecewise function over here. So what we have to do is to simply look at them part by part. Okay, and let's draw out the graph of fx first. For anything that is less than 0, we get minus x squared, which is this graph over here. For anything more than 0, we get 2x, which is this graph over here. So now let's try to find out what are the inverse functions for each of these components. For x less than 0, we let y equals to minus x squared, which gives us x equals to minus square root minus y, or positive square root negative y. But we have to reject this because x must be less than 0, and positive square root always gives us a positive value. At the same time, we will need to find out the domain of f inverse, which means the range of f for this particular component. And based on the graph, we know that y must be less than 0. Next, for x greater than or equals to 0, we let y equals to 2x. And this gives us x equals to y over 2. And for the domain of f inverse for this component, it will be the range of this portion over here, which therefore means that y must be more than or equals to 0. Now we simply have to interchange all the x and y values, and we will be able to get the inverse function, which is f inverse will be mapped onto x to give us a big curly bracket minus negative square root of negative x for x less than 0, which are from here and from here after we interchange x and y, and x over 2 for x more than or equals to 0, which are from here and from here after we interchange the x and y. Periodic functions are functions that repeat themselves at regular intervals. They can be inherently periodic, such as our trigonometric functions. For example, if we have the graph of y equals to sine x, we can see that for every 2 pi, this is a 2 pi cycle, this is another 2 pi cycle, and another 2 pi cycle. Here we can see that for every 2 pi, the graph repeats itself, and thus this is an example of a periodic function. Most functions are not periodic inherently. For example, we can have the function of fx equals to x for any domain. It will never be a periodic function. But we can convert it into a periodic function simply by number 1, limiting its domain, and number 2, introducing a second function of fx equals to x minus t, where t is the period of the periodic function. Now with this additional condition, we know that the graph can repeat itself for every t units. For example, I can have the function fx equals to x squared, which is clearly not a periodic function inherently, but if I can limit its domain into 0 to 2, and I say that it repeats itself for every 2 units, then it becomes a periodic function, which looks like this. So I'm first going to draw the repeating unit from 0 to 2. The y value will hit 4, and I'm going to exclude 0 because there is no equal sign over here. It will look like this for the repeating unit, and now I'm going to copy and paste this segment throughout for every 2 units. So at x equals to 2, it will be here. X equals to 4, it will be here. So I can join them using the same quadratic graph. From 4 to 6, same thing. like this. And I can do so for the negative portions from -2 to 0, this, -4 to -2, this, and so on. Periodic functions are frequently defined as piecewise functions. For example, we may have a piecewise function that is defined from 0 to 1, 1 to 2, and 2 to 3. So essentially, this function is only defined from 0 to 3. Thus, if we add in the periodic condition where fx is equal to fx minus 3, this entire function becomes a periodic function. In example 4, we now have a periodic piecewise function and we are asked to sketch the graph. So to sketch the graph, we will first draw out the base repeating unit. It is going to go from -1 to 0 and eventually to 3. And let's draw it bit by bit. Between -1 to 0, we get negative x squared plus 1. So it's going to look like this. Next, between 0 and 1, it is going to be e to the power of x. That means when x is 0, we get 1. And when x is 1, we get e. Let's say it is somewhere over here. It's 2.7. So we get this graph. And finally, between 1 to 3, it is just a constant e. That means it's just this horizontal line over here. And we have to exclude this endpoint over here because there is no equal sign for the end value over here. So based on this, we can now copy and paste this graph for our repeating units. We need to draw it from -3 to 7. So now let's draw from 3 to 7. So it is another 4 units from where we ended. So it is just nice another clone of this portion over here. So at 4 it is going to be at 1. At 5 it's going to be at E. And for 6 and 7, they are all going to be constant values at E. So we get this graph that looks like this. And for the other part, from -3 to -1, -2 here, -3 here, we can also imagine that for this portion, it should be the horizontal component rather than the curve component, and therefore it will look something like this. And of course, I forgot to include a circle over here just now for the endpoint. And thus, this is the graph of the periodic function, y equals to fx.